So the next parallel computing pattern that we're going to look at is also rather simple. And the idea is that you have a function that you apply to an arbitrary selection of input values to get the output value. So you have some inputs and you pick a selection of them to make up your final value. So essentially it's kind of like a function that picks the inputs from somewhere using a particular method and puts the output value back to where you want. Now, I've decided it's a good idea to stop insulting your intelligence with rather simplistic examples, so it's time to ramp up the level of challenge and look a little bit at a more realistic problems, shall we say. So in this example, I'm going to show the calculation of price of European options. An option is just for those of you who don't know, it's just a right to buy or sell an asset at a specific price and date. And this formula is actually calculated using some input parameters and variables, including these 5. So you would have a theoretical price of an option being calculated via the price at which the asset can be bought or sold, the price of the underlying asset right now, the time to expiration, the risk-free rate, and the so-called volatility. And the formula itself looks kind of like this. So this is a more interesting calculation than the one that we're already used to. And the interesting thing about all of this is this thing down at the bottom, the n of x calculation. That's the cumulative density function of a normal distribution. And it's an integral which doesn't have an analytical solution, but we can estimate it using the error function that's shown here. Let's actually jump into Visual Studio and program this thing. All right, here we go. So I'm going to call it Black-Scholes. Black-Scholes is actually one of the more popular examples when somebody wants to demo something in CUDA. That's what they use. So let me once again get rid of everything here. Don't worry, there won't be too much typing in this one. And we are going to look at new things in addition to just repeating the same calculations again and again. All right, so I'm going to start by once again defining the input values, and what I'm going to do is once again use the random generator. Let's for the sake of simplicity, we're not going to do any complicated thread subdivision here. Let's just define the number of elements that we want to price. Let's say 512, and then we can define the generator. So that's Courand generator T gen. Once again, I need the hash include for Courand. And yes, I do once again need to define the input libraries for both configurations, I guess. So, here we go. So courand.lib. There we go. Okay, so I've got Courand, I've got the generator. Let's initialize it once again. Courand create generator gen and Courand rng sudo once again the %wister will be our generator of choice. And what we're going to do now is we're going to essentially define the arrays that we're going to be feeding into the function. So I'm actually going to make a 2D array on the host side. So let's call it args, and that's going to be a essentially five arrays. So for I going from 0 to 5, what I'm going to do for each of these arrays is I'm going to malloc the array. So malloc args.I with I guess the size is going to be constant in size is count times size of float. So we'll use floating point values. So here I'm going to allocate them. So malloc args.I size of well, just size rather. Okay, and then I'm going to Courand generate uniform gen args.I and count. Strictly speaking, it shouldn't be uniform because, you know, the Black-Scholes model assumes geometric Brownian motion and whatever, but I'm going to just ignore this for now and just fill it with random data because we're trying to focus on the GPU computation side of things. So we're going to, we need 2 additional arrays on the GPU for the call and put values, so the prices at which the right to buy or sell is calculated, and those would be DC and DP, and we would CUDA-malloc both of them. CUDA-malloc, so DC, and that's size, and repeat for the put values. All right, so everything's allocated, and now we can actually call the pricing function. So that would be something like price, and then I would just use one block of count threads and provide each of the arrays. I'm not going to try and pack them into one array. It really doesn't matter because the gather pattern, you can kind of pick the data from where you want. So I would just specify them separately, and it's going to make it easier for us to distinguish what's what. So args0, args1, args2, args3, args4, and then the arrays to put the values in. So let's write the kernel now. Let's go up here, and we're going to define a kernel void price, which takes an array of strikes, an array of underlying values, an array of expirations, an array of risk-free rates, although, you know, in real life it wouldn't necessarily be like this, an array of volatilities, and an array for call values, and an array for put values. Now, if I start working with individual elements of these arrays, K, S, T, and whatever, I would have to keep writing S at IDX and P at IDX all over the place. So I'm not going to do it. I'm actually going to take out my calculation, so the formulae that you've seen previously, and I'm going to put them into a separate pricing function that takes single values. So what I'm going to do here, quite simply, is I'll calculate the thread index as thread idx.x, and then I'm going to call a device function, so which is also going to be called price. So I'm basically going to call it with k idx, s idx, t idx, r idx, v idx, and then provide the pointers to c idx and p idx. Actually, I'm going to change the name here slightly because well, no, actually then the name should be fine. Okay, so we need to create a function that runs on the device, and for that we would use a device specifier. So device, and notice that as I mentioned previously, you can have functions which are compiled for both device and the host. So I can say device host void price, and here I can have individual values, so I can have the k, s, t, r, v, and then 2 pointers for call and put values to output. Okay, so as you can see, this kernel is actually called from the CPU, runs on the GPU, whereas the device function is called from the GPU and runs on the GPU. So let's do this calculation quickly. I'm actually going to just cut and paste it from elsewhere because it's rather tedious, and I'm sure you can understand that there's nothing really super complicated here. So we have some complaints here from Visual Studio complaining that it doesn't know about these functions. So obviously some more headers are required, and I'm going to include those. Just a few. I know I need IOStream for the output. I'm going to include math.h. I'm going to include obviously. Well, I think that's it actually. So this is good. This should actually compile, and the only real issue is, you know, I've added these n calls here. And what exactly is n? Well, if we look back at the slides, you would see that even though n is actually an integral that doesn't have an analytic solution, you can redefine it in terms of an approximation using the error function. And this is one of the great things about CUDA, because CUDA actually gives you this error function to use. So all we have to do is we have to define another inline function. In this case, I can do an even more complicated thing. So here I've added host just to show that you can do it, but I'm also going to add another specifier here, device host inline. So inline is a hint that this function should be inlined as opposed to being added as a function call. So I'm going to call this n, returns a float, n, and takes a float x, and we're simply going to return 0.5 plus 0.5 times error function of x times, and then we need the 1 over square root of 2, which is m sqrt1 2, and I think this actually needs a definition here. So define use math defines. Yes, this way this should work. So let's try compiling this. And I'm not actually going to go into the details of running this and showing output, because I think we can all assume that this can be executed and verified to be running correctly. I just wanted to demo here the fact that you can have these function calls out of the kernel, and that you actually get to reuse some of the really cool math functions that CUDA gives you. And we could try going to the definition of error function just to see what it's like, really, because it's obviously like a redefinition of something. But what you see here is this is a kind of polynomial approximation with some of the predefined arguments that are being calculated. And you can also, if you go into these function definitions and you look at them, you would see it would always tell you where the calculation actually came from, and it would also show you some of the optimizations that CUDA is doing depending on the arguments and the executing conditions. So it's a good way to learn how CUDA actually does something in the background, although you would see references to something like internal fmat, and this perhaps should be explained because on certain GPUs the multiply and add operation is kind of compacted in the sense that it's one operation as opposed to two. So this is an internal optimization that CUDA is attempting to do to make your code even faster.